Now look at this, implicants. So before talking about implicants, let's talk about covering. So why is implicants important is when you're trying to derive the minimal expression for any given expression, we should find out all the subcubes which are called as essential prime implicants. So in order to find out essential prime implicants, you should first know what an implicant is, second you should know prime implicant, and third one is essential prime implicant, because these things play a key role in the minimization. So let's go step by step. So before talking about implicants, I want to talk about covering functions. So just see this. See, with this example, I'll tell you this and then I'll tell you this point. You please make a note of it later. See. Now, if you look at this, let us say it is a two variable function. In two variable function, how many minterms will be there? Totally 4. Therefore, 0, 1, 2, 3, 4 minterms are there. Let us define g to be a function which is having a 1 at 1, 0, 1, which means at this point it is having 1 and at all the other points it is having zeros, right? Now, if you look at f, the way f is defined, look at the way f is defined. F is having 1, 1 here and 0, 0 here. So, whenever g is 1, f is 1. So, you can say that f is actually covering g, which means inside f, all the minterms that are present in g are already present. Or if you look at this, f contains the minterm 0 and 1 and g contains the minterm only 1, which means whatever minterms are present in g are already present in f. That is the meaning of it, right? Now watch this. A switching function f, x1, x2, so on, xn is said to cover g, x1, x2, so on, x2 if f is superset of g, which means if f contains all the minterms which are already present in g, then it is called f is said to cover g. If f assumes true value whenever g does, right? So which means whenever g is having true value, f is having true, right? Now if f covers g, it means that f is superset of g, and at the same time if g covers f, then it means that g is superset of f. When will that happen? When both are actually equal sets, right? Then we can say that both are equivalent. So if f covers g and at the same time g covers f, then f and g are called equivalent. Watch this one. Now let us say g is this, then how many functions are possible which will cover g? In order to cover g, wherever g is having 1, we have to have 1. Therefore, I have kept 1 here, and all the others are optional. In the other places, either you could put 0 or 1. Therefore, how many functions are possible for f which are covering z is, in all the other possibilities, we have two chances, 2 into 2 into 2. Therefore, 8 functions are possible. In general, how can you find out number of functions covering a given function is, you find out all the minterms of the given function, and then in the covering function you put them as all ones, which means we don't have any choice there. In the remaining minterms, which means whichever are not there in g, let us say in the remaining minterms, the next function, the covering function could assume any two values. Therefore, it is 2 into 2 into so on, the remaining functions. Now let's see how to derive it. If g has x minterms and g is a function of n variables, if g is a function of n variables, how many elements will be there in this minterm? How many elements will be there in this table? If g is a function of n variables, 2 power n elements will be there, right? And out of which g is already choosing x minterms. Therefore, how many remaining elements will be there for f to choose? All these x terms, whichever are present in g, should already be present in f. Therefore, f does not have really any choice on x. Therefore, f has choice only on 2 power n minus x, which means in the remaining minterms, whichever g left out, f can assume any two values. Therefore, 2 into 2 into so on these many times. So this is the total number of functions which will cover a function g, given that both the functions are in n variables and then g has x minterms, right? It is simple to derive, I think. See, wherever g is 1, f has to be 1. Therefore, I am putting in there 1. And wherever g is 0, there f could assume anything. Then how many max terms are there in g, which is nothing but how many zeros are there in g? 2 power n minus x. Now all these chances at all these locations, f can assume either 0 or 1. Therefore 2 power n minus x. Got it? So these many functions are going to cover g, given any g. And see this example. I'll just show you. I'll just try to solve it. if f of x equal to wx plus yz, if this is the expression given, then how many functions will be covering f? In order to understand how many functions covering f, you have to understand how many minterms are there in f. So first of all, how many minterms are possible with 4 variables? The total number of minterms possible are 16, right? Now let's see, out of this 16, how many minterms has f already chosen? How can we get it? Given the function, convert it to canonical form, canonical SOPs form, sum of products form. Now in this wx, 2 terms are missing. What are they? Y and z, right? So wx is present here, y and z is present here, which means wx followed by yz, and now we don't have 2 terms. Those 2 terms can assume any value, which means 0, 0, 0, 1, 1, 0, 1, 1. So what we could do is, in place of w and x, we could have 1, 1. The reason is both are non-complemented. See, I am telling you a method by which you can quickly arrive at the minterms, number of minterms present in a function. See, in place of wx I am putting 0, 0, and in place of y and z you have 4 combinations. Therefore 1, 1, 0, 0 or 1, 1, 0, 1 or 1, 1, 1, 0 or 1, 1, 1, 1. These are all the 4 combinations for, or they are all the minterms which are we generated from wx. And then yz, y and z are here, w and x are here. Therefore y and z is 1, 1, and then wx can take any number of choices. Therefore 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, right? So this is how you can expand it. So maybe you could keep it in mind. So whenever you want to expand it into sum of products, canonical sum of products, you just take the min term or the product term and you just write the combination for it, and in the remaining combinations, whatever is remaining, which means how many variables are remaining, in those combinations you try to put all the combinations in their positions, right? Now you see that it is already repeated and all the others are unique. See, 1, 1, 0, 0 is not repeated, and 1, 1, 0, 1 is not repeated, 1, 1, 1, 0 is not repeated, 1, 1, 1 is not repeated. So they are all unique. So how many minterms are present in f? F is already containing, out of 16 minterms which are possible, f is already containing 7 minterms. Therefore f is not containing 9, right? So what happens if any function has to cover f? That function has to have all these 7 minterms. Along with that, it should have 9 more minterms. It could have any of the 9 more minterms, right? Or in case of subset set theory also, you could think of it this way. If a set is already containing 7 elements, then how many sets are going to be superset of this set? That is same thing, right? If the set is already containing 7 elements, the superset of it should also contain 7 elements. Then how many elements are remaining? 9 elements. In these 9 elements, the remaining set, the set which is going to cover this set, can take any value, which means the number of power sets possible with 9 elements, which is nothing but 2 power 9. Or if you didn't understand this, see, already f is having 7 minterms. Therefore the function which is covering f should also have all the 7 minterms, which means all the ones at the 7 locations. And how many locations are remaining? 9 locations. In those 9 locations, it could have 2 possibilities, right? Therefore 2 into 2 into 2 into 9 times. So 2 power 9 is the total number of functions which are capable of covering f. Anyway, we could find out the number of functions covering it, but my main intention in teaching about all this is to know about the implicant. So now let's talk about the implicant, and then prime implicant, and then essential prime implicant, and then minimization. Okay.